Hi everyone, in this video we're going to go through the remainder of the notes for section 15.3. We start out with an example where we have to find the volume of a region bounded by two different paraboloids. This actually mirrors the problem in section 15.2 that I kind of cut short because it results in some pretty ugly calculations. Okay, that's what necessitates the use of polar coordinates for these double integrals. Okay, so we've got our lower parabola, the parabola that opens upward, z equals x squared plus y squared. The parabola shifted 8 units up and opens downward. Excuse me, paraboloid, z equals 8 minus x squared minus y squared. What we showed previously was that they intersect in a circle of radius 2. We could also do that using polar coordinates. I can rewrite my first paraboloid, x squared plus y squared equals r squared, and my second paraboloid, this is 8 minus x squared plus y squared, so factor out that negative, and then we have z equals 8 minus r squared. Okay, so there we have our two paraboloids in polar coordinates. To find the region of integration, the region of that we're going to integrate over, we can set our 8 minus r squared equal to r squared. Where do these two paraboloids intersect each other? That would give us 2r squared equals 8, r squared equals 4, and then r equals 2. R squared equals 4, r equals 2. Those are circles with a radius of 2. Okay, so that allows us to set up our integral to find the volume of our region is the double integral over r of the top paraboloid, which is 8 minus r squared, minus the bottom paraboloid, which is just r squared, and then r dr d theta. Okay, the bounds for our integral are first on the outer from 0 to 2 pi, because it's the full paraboloid, and then the inner bounds, the r bounds, are from 0 to 2. The radius of this circle, the region r, is 2. And then simplifying inside of the integrand, we have 8r, so we're distributing the r, and then minus 2r squared, but then distribute the r gives us 2r cubed, dr d theta. And that right there is pretty standard to then go through and evaluate. So working on the inside first, integrating with respect to r, 8r squared over 2 gives us 4r squared, minus 2r to the fourth over 4 would give us r to the fourth over 2 when you simplify. That gets evaluated over the bounds from 0 to 2, and then integrated in terms of theta. Substituting in the top bound, we would get, 4 times 2 squared is 16. 2 to the fourth is also 16. Over 2 is 8. So I believe when all said and done with the top bound, you get 8. And then the bottom bound, of course, gives you 0. So we're just integrating 8 in terms of theta, which is 8 theta, evaluated from 0 to 2 pi, which gives us 16 pi as the volume of that region, which is the same as I wrote in the previous section, but it doesn't give it as much clout because I didn't actually go through all of the calculation, because it would have been a mess. But that's why, and you can see polar is just, it's just better to set up these double integrals when our regions are round. It just kind of makes sense this way. In our next example, we are looking at what is called an annular region, also known as ring-shaped. And the reason that this one is ring-shaped is because when we look at our region R in the problem, our R bounds are from 2 to 4, so this one doesn't go all the way to the origin. So we end up with a region that is the shape of a ring. So we're finding the volume of the region beneath the surface z equals xy plus 10, and above our region R, where our R bounds are from 2 to 4, theta bounds are from 0 to 2 pi. This one is pretty standard to substitute into our double integral. So we set this up. Our theta bounds are from 0 to 2 pi. Our R bounds are from 2 to 4. Oh, and we're finding a volume here. And our region of the function is z equals xy plus 10. But if I start to write in xy plus 10 in there, I'm going to be mistaken because we're integrating in using polar coordinates, right? We have r, dr, d theta. So we need to take a couple of steps here and rewrite those our equation in polar coordinates. To do that, we take our z equals xy plus 10, and we substitute x is r times the cosine of theta, and y is r times the sine of theta, and then plus 10. And that simplifies to z equals r squared. And we've got this sine theta, cosine theta there, plus 10. We could leave it as that, and later on in the problem, we'll ultimately just have to make a u substitution. So again, it would be perfectly reasonable to leave it as sine theta, cosine theta. Later in the problem, I'll have a u substitution. But we can also use the double angle identity, which will allow us to kind of push the sine and cosine theta together. And we end up with 1/2 r squared sine of 2 theta plus 10. Off to the side here, I'll just write the identity that I used. It's the sine of 2 theta equals 2 sine theta cosine theta. And because we had a sine theta cos theta, that's why we had the 1/2 out in front. I didn't have to make that substitution, but it'll ultimately make later on a little bit easier. Okay, so that will substitute in for our function. 1/2 r squared sine theta plus 10. Okay, so our next step, we're going to distribute that r into the parentheses. So we have the integral from 0 to 2 pi, and then the integral from 2 to 4, 1/2 r squared sine of 2 theta. Oh, that should be an r cubed. Oh, I just noticed 2 mistakes. That should be an r cubed sine 2 theta, and I lost my 2 in the previous step. That was a sine of 2 theta. Plus 10r dr d theta. And now just going through our integration, 0 to 2 pi. R cubed is r to the 4th over 4, so we have 1/8 r to the 4th sine 2 theta plus 10r squared over 2, or 5r squared. And that gets evaluated from 2 to 4 d theta. When you substitute top bound minus bottom bound there, we have that our volume is from 0 to 2 pi. Excuse me. We end up with 30 sine 2 theta and plus 60 d theta. So I'm skipping the computational step there. Excuse me. Finally, last step in this integration is to integrate our sine 2 theta. That would be negative 1/2 cosine 2 theta. So that 30 turns into a 15 cosine 2 theta plus 60 theta. And that gets evaluated from 0 to 2 pi. And when the computation of this one is all said and done, we have 120 pi as the volume of that region. And on the next slide here, we can look at what this region actually looks like. So first, the picture on the left here, this is our region R from 0 to 2 pi, so it's a full revolution, and from 2 to 4, that's why it's annular or ring-shaped. But then when you put that, look at the z equals xy plus 10 over that region, this is what we actually found the volume of this solid underneath, this kind of saddle-looking shape. So it's a saddle with the hole cut out in the center, I suppose. Oh, it's a Pringle if you very carefully remove a circle out of the center. That's what I'm going to go with for the visual here. Okay, so that's just a quick little visual of what we're looking at in that problem. Theorem 15.4 on the next slide states just a double integral theorem for more general polar regions, so when the regions are not necessarily rectangular. So instead of our r bounds being constant, we have our r bounds are some function of theta, and our theta bounds are still in fact constant. The setup is pretty much the same, our function times r dr d theta, But again, instead of the r bounds being constants from a to b, 0 to 2, 2 to 4, they're some function of theta. And so we'll look at an example involving that. And in this last example for the section, we are told to write an integral. First of all, when it says write an integral, that means we're not going to be evaluating it, but simply just write an integral for the region outside of the circle r equals 2 and inside r equals 4 cos theta. And r equals 4 cos theta, if you didn't know, it's okay. That is also a circle. So r equals 4 cosine theta is this red circle here. R equals 2 is our circle of radius 2 centered at the origin. So if I'm going to shade the region that we're talking about outside of the circle centered at the origin, inside of the other circle, we're talking about this region right here. Okay, so we need to set up a double integral that will find that will use that shaded yellow area as its region R. So if I just draw my integral first, we've got to figure out what the theta bounds are and what the r bounds are. And then my function, I don't have one, f of r comma theta, r dr d theta. So that I can kind of do without thinking, but now I've got to do some careful thought in the next step. Okay, so maybe we talk about the r bounds first. Okay, what is the inside radius of this region and what is the outside radius of this region? So if we think about it, right, what I've just drawn in black there, that's not part of the region, but starting right on the blue circle, that's the inside of the region, and then the outside of the region is the red circle. Okay, so what that means is that my r bounds, the lower r bound, the inner radius, is r equals 2, and the outer radius, the outside r bound, the upper r bound, is r equals 4 cosine theta. 2 being the equation of the inner circle, 4 cosine theta being the equation of the outer circle. Okay, so that's how we first can kind of think about our r bounds. And anywhere in the region, even if I draw my little dotted line down here, the inner radius is r equals 2, and the outer radius is r equals 4 cos theta. So that holds for any part of the yellow shaded region. Okay, that's step 1. Step 2, now we've got to figure out our theta bounds. We've up until this point been using 0 to 2 pi, 0 to 2 pi. Well, that's not the case here. If I were to use r equals 0 or theta equals 0, that's the positive x-axis. Out to 2 pi, that would be a full like that. That's not the case here. If you think about it, the yellow shaded region is trapped between this line. Oh, I kind of missed there, and it is also trapped between this line, if I had just drawn them in the right spot. Let me see if I can move that one right there. And this first one, see if I can fix that. There, perfect. Okay, so the yellow shaded region is trapped between those two angles, those two arcs there. And so what we've got to do is find out the point of intersection of the two circles. Okay, so hopefully you agree that the yellow is between the two lines that I just drew. Okay, the two lines are determined by where our two circles intersect. Okay, so what we can do is we can take our r equals 2 and our r equals 4 cosine theta, set them equal to each other. That tells me that cosine theta is equal to 1/2, and the angle whose cosine is 1/2, check it in your calculator if you need to, is pi over 3, and because I know I need to find an angle in the fourth quadrant, it's also negative pi over 3. Again, feel free to check these in your calculator. Okay, so that actually is how we determine the theta bounds in this problem. Okay, first it's a matter of finding out where the region is, what it's defined by, and then how do I find that value? Do I need to set the two curves equal to each other? Do I need to use is it one of the axes? Like that's kind of what we're going to have to figure out as we do these problems. Okay, so that gives me my theta bounds, negative pi over 3 up to positive pi thirds. Okay, so for part B now, we need to find the region inside of both circles in part A. So inside of the blue circle and inside of the red circle is this yellow shaded region. Plus there's a little sliver in that yellow shaded region and a little tiny sliver in up there also. Okay, and because of those little slivers, this part is actually a little bit more involved. But what we need to do to the first part of the answer is actually not too terrible, and I'll run through that first. So to set up our first integral, our first double integral, we're going to take, well, let me first write the general part first. F of r comma theta r dr d theta. Okay, so what I'm looking at now is between my black lines, this one and this one. Those were at pi over 3 and negative pi over 3, remember? So I've got this yellow region here, this yellow region here. It's between the black lines. Its outer radius is r equals 2. Its inner radius is r equals 0. And its theta bounds I've already clearly kind of stated already. So that one is, ready? 0 to 2, negative pi over 3, up to positive pi over 3. Done, call it a day. But that's not all. Done with that region. Okay, so that's the first piece. All right, hopefully that part made sense. If you worked through part A, hopefully that made sense. But now for the next part, we've got this little sliver of a yellow region and this little sliver of a yellow region. And that is a little bit more challenging. But what we end up needing for those two regions is two more double integrals, or iterated integrals. Let me just write the general form first. And then one more time. Copy and paste it. There we go. And I actually could just write it once and then double it, but just for the sake of writing it down. Now let's talk about the radii first. The inner radius, though, that little yellow sliver of a region, goes down to the origin and goes out. The outer radius is on the red circle. So the bounds are, the r bounds are from 0 to 4 cosine theta for the top region, and similar for the bottom region. It starts at 0 and goes out to the red circle, so 0 to 4 cosine theta. Now the theta bounds, and this is the most challenging part to grasp, I think. The theta bounds start at our pi over 3 line. My circle's getting pretty messy here, or my picture is. Start at the pi over 3 line, so my bottom theta bound is pi over 3, and they actually, my theta bounds go up to pi over 2. Pi over 3 up to pi over 2. The yellow region is between those two angles. Similarly, down below, the yellow region is between negative pi over 3 and negative pi over 2, even though you can't really see it anymore because my picture got really messy. So this one is negative pi over 2 to negative pi over 3. Last part was a little bit more challenging, but take a look at it. I left the next two slides have just better images of what I drew. I could have written over those, but I chose to draw the pictures myself just to show you that you can draw them as well. Oh, and finally, sorry, we would add all these three regions together. But that is the end of the notes for this section. Hopefully that made sense, but if you do have further questions, make sure that you shoot me an email or ask something in class on Friday. Thank you for listening. Bye.